Okay, welcome back to the online course on embedded system design verification and test. We have discussed about the temporal logic and in particular about CTL, computation tree logic, and we have seen how some of the property can be expressed with the help of your computational tree logic. Now we are going to look for a verification method which is known as model checking. So model checking is a method by which we can check the correctness of a property specified in CTL in a model. Okay. So what is the verification techniques? Basically we are going to verify the specification of a given system in the design or the abstract design that we have come up. Okay. So today we are going to discuss about the model checking, which is a verification technique. So what are the process of model checking? So basically already we have mentioned that in verification technique basically we have one component which is known as the system model. We are designing our system and we have to represent our system with the help of some formal mechanism, and generally we use some finite state machine to represent our system. So we need one model of our system and the model will be represented with the help of Kripke structure. Kripke structure is nothing but some sort of a finite state machine that already we have seen, and the specification of the system will be given or represented with the help of some property specification logic, and in our case we have discussed about CTL, computational tree logic. Okay. Now first we are going to have the model of our system, then we are going to write our specification or property in some formal way, and finally we are going to have a verification method, and in our verification method we are going to talk about model checking algorithm. Okay. Today we are going to discuss about this model checking algorithm, how we are going to verify the property specified or written in CTL and going to check the truth of this property in a model that we have designed for our system. So now how we can visualize the model checking algorithm? So one way you can say that given the model M and the CTL formula phi and a state S0 of S. So here we are going to have three input. We are going to talk about the model M, we are going to talk about one CTL formula and a particular state S0 or maybe Si of the system. So these three will be input to our model checking algorithm. So what model checking algorithm says? It is going to give me yes if the property phi is true in the state S0 of model M, or otherwise it will say no if this property does not hold in that particular state S0 of the model M. This is one way we can represent it. What are the inputs? It is having three inputs: model M, state of a model, and a property. And what model checking algorithms or method gives us? It says yes if the property is true in the state S0, or it says no if the property is not true in the state S0. So these are the outcome of our model checking algorithm. That model checking algorithm can be again treated in a different way. So in this case what we are going to say? We are going to give a model M and a CTL formula phi. So we are having a method, model checking method. What are the inputs? Model M and the specification written in our CTL formula phi. Now what model checking algorithm gives? It gives us all the states of model M which satisfies phi. So in the model M we are going to check for the property phi, and as a result this model checking algorithm gives us the all the states where this particular formula is true. So we are going to discuss this particular approach, that we are going to give a model M and a formula phi, and this method, model checking method, returns us all the state where the given formula phi is true. So basically this approach is nothing but some sort of labeling algorithm. We can say we are going to label each and every state with the help of the given CTL formula if the CTL formula is true at that particular state. So, basically this model checking algorithm is nothing but a kind of your labeling algorithm. We are going to label it. So, if say if this is a model, some sort of model that we have, okay, and say phi is a formula. If phi is true in this particular state, then we are going to label this state with this particular given formula phi. Okay. Now, we will see how we are going to label this particular phi, or how we are going to check the truth values of this particular phi. If the truth values of the phi is true in this particular state, say Si, then it will be labeled by phi. On the other hand, now this as a result, this labeling algorithm is going to return this particular set Si as a set of state where a given formula phi is true. So, now we are saying that CTL model checking algorithm basically works by iteratively determining or labeling state which satisfies the given formula phi. So, iteratively it will going to check each and every state, and if the formula is true, then it will label with that particular formula, and after labeling all the states, it is going to return as a state of states where we have the label of phi, that means where the state where the formula phi is true. So, the input is the given model M and the CTL formula phi, and it returns what is the output, set of state of M where which satisfy phi. So, two inputs we are giving, and as a result, as an output we are getting a set of state. Now, what we are going to look for labeling algorithm? Already we have discussed that in CTL we are having temporal operators, and temporal operators are preceded by path quantifier A and E, and we are having several CTL operators, but already we have said that there is an adequate set of operators. With the help of this adequate set of operators, other operators can be derived. So, in this particular case, we are going to look for the adequate set of operators as your AF in all path in future phi, EU there exists a path with until operator, and EX there exists a path in next step. So, these are the three basic operators. We are going to look into it, and we are going to find out a method to check for the truth of this particular formula in a given model. Now, in this particular case, what will happen? If we give any formula phi, then we are going to convert this particular formula, or we are going to get an equivalent formula for phi, which involves only these three temporal operators AF, EX and EU, because this is the your adequate set of temporal operator we are considering. And along with that, logical connectives, because we may have that conjunction, disjunction, conjunction, implication, all those logical connectives we have, and along with that root value true or top. So, if suppose psi is a subformula of phi, and state satisfying all the immediate subformulas of psi have already been labeled. Now, we are going by level, or we can say that if it is a given formula, we are going from all the sub formulas. First, we have to look for the primitive one, and how we are going to get the primitive one, we will discuss about it, and we know about the labeling function of our model, because the model consists of a labeling function also, because this is a set of state, this is a transition relation, and L is a labeling function. With the help of labeling function, we know the truth values of atomic proposition in the states. Okay. So, now if phi is a formula, then phi can compose of several sub formulas. Now, we have to look for each and every sub formula, and if we know the truth values of a sub formula, then only we can look for the truth values of the given formula. So, as for example, I can say that if I say that A, G, there exists a path in future P. Okay. So, in this particular formula, what we are talking about, the notion of sub formula, P is a atomic proposition. So, P itself is a sub formula, and P is an atomic formula. So, it is a CTL formula. So, EFP is another CTL formula, because if I know that if phi is a CTL formula, then EF phi is also a CTL formula. Now AG EFP is the CTL formula, because if phi is a CTL formula, then AG phi is also a CTL formula. So in this particular case, if phi, this is the given formula, then what are the sub formulas we are getting over here? P is a CTL formula, which is a sub formula of this given CTL formula. Then second one is your EFP, which is another sub formula, and this is the given entire formula. So to find out the truth values of phi, first of all we have to know the truth values of this sub formula EFP. Also, to know the truth values of this particular sub formula EFP, we must know the truth values of this particular P, the atomic proposition. So this is the atomic proposition, and atomic proposition is going to take truth values either true and false. Okay. So in this particular case, you just see how we are going to get the truth values of P through the leveling function, because in our model we are having a leveling function, and we are going to level the states where the atomic proposition is true. So we know the state of states where the truth value of P is true. Now with the help of these things, now we are going to find out EFP, because we know the truth values of P, so we can find out the state of state where the truth values is true for this particular formula EFP. When we know the truth values of this particular EFP, that means if we know the state of state where this particular sub formula EFP is true, then we can look for that state of state where the given formula AG EFP is true. So we are going level by level, or say sub formula by sub formula, to look for the truth values of a given CTL formula. So already I have mentioned about this formula and sub formulas, because I have already mentioned about, say, if I can say like that, another sub formula if I take in all part globally P implies there exists a part in future P or Q. Okay. So in this particular case, you just see we are having atomic proposition P and Q. So these are the sub formulas. We know the state of state where these two sub formulas are true, or the atomic proposition P and Q are true. We know these things with the help of leveling function. Since P and Q are your atomic proposition, so P or Q is also atomic proposition. If we know the truth values of P and Q, then we can find out the truth values of P and Q, and we will be knowing the state of state where this particular P and Q is true. Now if you know the truth values of P and Q, or the state of state where P and Q is true, P or Q is true, then we can look for the truth values of EF, P or Q. So once we know the state of state where EF, P or Q is true, then we can look for the state of state where the sub formula EF, P or Q. So once we know the state of state where this particular sub formula is true, then we can look for the state of states where AG P implies there exists a part in future P or Q is true. So these are the atomic proposition. Then we are going to look for the sub formula P or Q, then EF P or Q, then P implies EF P or Q, and finally AG P implies EF P or Q. So now what is that model seeking algorithm, CTL model seeking algorithm? So we are going to have a function called set of phi. So this is basically satisfiable function, and what is the input? A CTL formula. Okay. So we are going to now find out the state of states where this particular given formula is true, and we are going to look for some operators only which is adequate to express all other CTL operators. So that's why you are saying that in that particular case we say that if phi is top, already I said that top is nothing but the truth value true, and bottom is nothing but the truth value false. Okay. So it says that if phi is the top, truth value true, which is a constant, then it returns this particular all states, because in all state truth value true is true. If the given given formula phi is your bottom, that means truth value false, then it will returns the null set, because in none of the state false is true. So, if phi is an atomic proposition, then what it returns? It returns all the states where phi is a member of the labeling function. Okay, we know. Then if it is your phi is not of phi 1, then it returns S minus satisfiability of phi 1, because not of phi is negation of the phi. If in some state phi is true, then in remaining state not of phi is true. So, it is going to return S minus satisfiability of phi 1. Similarly, these are simple n connective. So, satisfiability phi, the state of state where phi 1 is true, intersection set of state where phi 2 is true, or so this is your union set of state where phi 1 is true, or union set of state where phi 2 is true. So, phi 1 implies phi 2, then this is basically not of phi 1 or phi 2, this is the equivalent. So, we are going to find out the set of state where not of phi 1 or phi 2 is true. Ax phi 1, then we know that Ax phi 1 can be expressed with not of Ex not of phi 1. So, in that particular case, we have to first write this expression with its equivalent expression. Now, we have to find out the truth values. We are going to look for the set of state where this particular formula is true. So, here we are having one sub formula not of phi 1, then Ex phi 1, then not of Ex phi 1. So, if phi is Ex phi 1, then it is going to return a satisfiability Ex phi 1. So, this is a method we must have, and we are going to discuss about this method. Similarly, if phi is A phi 1 until phi 2, then we are going to look for the equivalence of this A phi 1 until phi 2, which is expressed with the help of there exist, with, until and globally. So, first A phi 1 until phi 2 will be represented with the help of sub formula, and we are going to look for the truth values of this particular formula. E phi 1 until phi 2. So, we have to get the method to find out the state of state where E phi 1 until phi 2 is true. Similarly, Ef phi 1, it will be represented its equivalent formula. Eg phi 1, it will be represented with its equivalent formula. If Af phi 1, then we must have a method for Af where it is going to return a set of state where phi 1 is true. And for Ag phi 1, again we are going to look for the equivalent of this particular formula. So, basically you just see we are talking about Ex, Eu and Af. These are the three operators which is the adequate set of operators. So, we are going to discuss about the methods to check for the truth values of these three operators in a given model, and by this case what we are going to say that we are going to label the set of states or label the states where this particular formula is true, and finally we can return those particular states by talking about that these formulas are true on those particular states. So, we are going to discuss about these three methods. So, how already we have discussed how we are going to talk about atomic proposition. It will be true in a set of states, in a state S, if P is a member of this particular labeling function. Similarly, logical connectives already have said that if we know the state S, if state is labeled with P and Q, then already we have to say that those states are labeled with P and Q. So, if this state is labeled with P and Q, that means if both P and Q is true over here, then we can label it with P and Q. This is the notion basically. So, like that other connectives also you can see. Now, we are going to basically discuss about the temporal operators. So, first one is your exp. There exists a path in next state P is true. So, label any state with exp if one of its successor is labeled with P. Now, say first of all, if we are going to consider about any system and if we are going to look for this particular formula exp, then what will happen? First of all, we must know the level of this particular atomic proposition P. Just see that if I am going to say that these are the two states where P is true, and in all other states P is false. So, according to the definition of exp, we know that exp will be true in this particular state because there exists a next state where P is true, and similarly exp will be true over here. So, that means after looking for the truth values of exp, it is going to label these two states with the formula exp. Okay. Or on the other hand, we can say that at the end of this particular algorithm, it is going to return these two states and says that in these two states exp is true. Now, how we are going to implement it, or going to get a method for exp. So, the function exp we are going to define now. So, it is going to look for the state of state where P is satisfying, where P is true. P may be now in any CTL formula. It may not be atomic proposition, it may be any CTL formula, because already I have said that if my CTL formula phi is your P and Q, then first of all we must know about the truth values of P and Q, and once we know the truth values of P and Q, then we know the truth values of P and Q, or we know the state of state where P and Q is true. So, this P is any CTL formula. Now, determine the state of state that satisfying exp. Now, what we are going to say? We are going to take two set x and y. These are the variables, local variable x and y. Now, what we are going to say? First, x is nothing but a set of state where P is true. So, we know that if in the given model, already in the last slide also I have mentioned, if it is marked say Si and Sj is marked with P or labeled with P, then satisfiability of P is going to give me the set of state Si, Sj. Then we are going to now collect the states Y. What we are going to Y? We are going to collect the state S0 belongs to S. So, belongs to this particular state space. Now, what are the properties of this S0? It says that we are having a transition from S0 to S1. We are going to have a transition from S0 to S1 for some S1 belongs to X. Now, in this particular case, this is X. Okay. Set of state where P is true. So, Si and Sj is going to have X. Now, we are going to look for such type of space S0 where I am having a transition from S0 to any of the state of this particular Si or Sj. So, if this is Xk, then what will happen? At least we are going to get one transition. Next state is your Ss. So, I am having this Sk to Si such that in Si P is true. So, Sk will come return it. Similarly, this particular state will also come into picture, because from here at least I am going to get one state where P is true, but if I am going to look into this particular state, then it will not come into picture, because in the next state P is not true. So, it is going to return those particular states, and finally, we are going to return Y. So, what it basically does? It is going to return me the set of states where exp is true. We are looking for the formula exp. Okay. So, this is the way that we can say. This is a very simple one. How we are doing it? So, by looking into the model. Model is nothing but some sort of finite state machine, which is basically similar to a graph. So, it is a nothing but a graph traversal algorithm. First, we are collecting those particular set of states where the given formula is true. Then, we are just looking for its predecessors, and we are collecting all the predecessors, and we are returning those particular predecessors. So, these are the state of state where exp is true. So, already I have explained example. Now, second temporal operator I am going to say AFP in all part in future P holds. So, in that particular case you just say how we are going to do it. If any state S is labeled with P, then label it with AFP. So, if any state P is true, then I am going to label it with AFP. Why we are doing it? Because as per our defined semantics, in our defined semantics what we are saying that future includes present. Okay. Since future includes the present behavior, so that is why I can say that AFP is true over here. Then what we are doing, wherever P is true we are labeling with AFP. Then we are saying repeat, label any state with AFP if all successor states are labeled with AFP. Okay. So, if it is labeled with AFP, then I can label this one also AFP provided all its successors are labeled with AFP until there is no sense. Until there is no sense, what does it mean? So, first I am starting from this one, then I am collecting this state, then I am going to look for its predecessor and I am going to look for all the transition of the given graph, and if we cannot add any more state, then we stop there. So, repeat until any sense means until there is no sense, that means we are not going to get any new more states. Okay. So, how we are doing it? So, why it is possible? So, basically already we have discussed about the equivalence. AFP is equivalent to your P or AX AFP. If P is true in the state, then we can say that AFP is true, or if P is not true in a particular state, then I have to see AX AFP must be true in that particular state. So, every iteration we are going to collect more and more states, and finally, if we cannot connect any more states, then we are going to stop our algorithm at that particular point. So, that is why it says until there is no sense. So, now with example I am going to just give you. So, if this is the scenario, first I am having these are the states where P is true, then in the next set I am going to say that AFP is true in this particular 3 state as per my first behavior. Okay, so these are the states where AFP is true. Now, we are going to traverse this particular graph, and what we are going to say, since all this particular 3 state AFP is true and this state is having only 3 successor, so we can label it with AFP. So, like that we will go step by step and we will traverse the entire graph, and finally we will find that in all the states it will be labeled with AFP wherever AFP is true, and it will not label those states where AFP is not true. So, this is the Cripps method what we are saying. So, we are starting with one particular state, X is nothing but we are going to take entire state space, that 2 local variables we are using X and Y. X is initialized to entire state space, and what is Y? Y is initialized to the set of state where P is true. So, we are using this particular satisfiability function that we have defined, and we know the truth values of P in a model. So, we are going to collect all the states where P is true. So, this is the state space set Y. Now, repeat until X equal to Y. So, initially it is the entire state space and Y is a subset of it, they are not equal. So, we are going to begin it. So, we are going to enter into this particular loop. Now, we make X equal to Y. Okay. So, wherever P is true, we are going to put it in X for our requirement, and Y. Now, we are going to append Y. So, first we know that if in a state P is true, then in that particular state AFP is also true. Now, we have to see, going to collect more states, and what we are doing. So, it is Y union, we are going to collect states S, and what type of states we are going to collect? For all S dash with there is a transition from S to S dash where S dash belongs to Y. Okay, that means such type of state we are going to collect. Say if I am having this particular scenario, if these are the states where AFP is true, okay, then we are going to check such type of state as such that form as we are having a transition to some S dash and where S dash belongs to this particular state Y. That means already AFP is true on this particular state, and we repeat this particular loop when X becomes equal to Y. That means we cannot add any more new state to this particular set of state Y. So, until no sense we are going to repeat these things, and finally it will return Y. That means it is going to return the state of states where the given formula AFP is true. Okay. So, this is the future one. So, another temporal operator that we have E, P until Q. So, here exists a path P remains true until Q becomes true. So, for this you just see I am having two sub formula P and Q. So, before going to look for the truth values of E, P until Q, you must know the truth values of P as well as Q. That means it is we must know the state of states where these two sub formulas are true. So, if any state S is labeled with Q, then label it with E, P until Q. And after that you repeat label any state with E, P until Q if it is labeled with P, and at least one of its successor is labeled with E, P until Q, until there is no sense. Again this is same notion that we are going to traverse the entire state space and we are going to collect the states one after another where it is going to satisfy this particular property, and basically this is nothing but already we have seen this particular equivalence where E, P until Q will be true in the states if Q is true itself, okay, or it is going to satisfy this particular property P and EX E P until Q. So, in there exists a path in next state E, P until Q is true. So, this is the notion that we are having about this particular E, P until Q. So, if Q is true in a particular state, then we say that E, P until Q will be true. So, we are going to collect those particular states, or it should satisfy this property P must be true in that particular state and there exists at least one path in such that E, P until Q is true in the next state. This is EXP. Okay. So, this is the scenario. If say that in this particular case if I am having this particular label, then you see Q is true over here. Since Q is true over here, I can very well mark this particular state is E, P until Q, because if P is true then E, P until Q is true. So, here since Q is true over here, so you can label with E, P until Q. Okay. Then what will happen? Now, this is the scenario. Then if this is labeled with your P, E, P until Q and Q, and this is P, then what will happen in this particular case? In this particular state P is true and P and there must exist one next state where E, P until Q is true. So, we are going to label this particular state also E, P until Q. Okay. Like that we are going to traverse the entire state space to find out the state of state where E, P until Q is true. So, for that we are having this particular algorithm. So, what we are going to look? We are using three local variable W, X, Y. What is W? W is nothing but a state of state where P is true. So, we are collecting the state of state where P is true, because we need in our algorithm, because if P is true over here, then only we can look for E, P until Q is whether it is true in this particular state or not. So, that is why we are collecting all the state of state where P is true, and X is basically initialized to entire state space, because my states will grow up to that level if the formula is true in all the states. And what is Y? It is nothing but a state of state where Q is true. Now, we are getting Y, set of state where Q is true, and we know that wherever Q is true in those particular state, E, P until Q is true. Okay. So, for that these are the initial state of state where E p until q is true. Now, we are going to repeat until x equal to y. So, initially x is the entire state space and y is the state of state where q is true. So, in that particular case initially it will be false, then we are going into this particular loop. So, for our region x will now assign to y, because in next iteration we are going to check whether y remains same or we are added some more new states to it, because in the next statement y is equal to y union something. Okay. That means whatever y we are having, either we are going to add some new more states, or if cannot add any new more states, then y remain as x. Okay. In that case it will going to satisfy x equal to y. So, what are the states we are going to include? So, what is W? W is nothing but set of state where P is true. So, this particular state we are taking, because if P is true in a particular state, then only E P until Q having a chance to be true in that particular state. Okay. If P is false itself, then we cannot say, because if it is having something like that, if Q is true over here, then E P until Q true is over in this particular state as per our differentiability. But if P is true over here, then only you can see that E P until Q becomes true at that particular point. Similarly, if I am having another transition from another state and if P is not true over here, then it is not a potential candidate, or it is not a state where E P until Q will be true. Okay. So, that is why we are going to look for all the states where P is true. Along with that, we are going to see such type of states, going to collect these particular states as such that there exists S dash where we are having a transition from S to S dash. Okay. And S dash belongs to Y. What is that Y? Y is nothing but satisfaction of Q, or maybe state of state where P until Q is true. In this scenario, I am getting these two states Si and Sj, from where I am having a transition to this particular state where E P until Q is true. Okay. But so, this particular component is going to give me Si and Sj. Now, this subset will be having an intersection with W. When I am going to intersect with W, in W Si will not be present, because here P is not true, but Sj will be present. So, after intersecting that thing, we are getting Sj. So, Sj will be appended to Y, because it is Y union something. So, that means this particular state is appended, then again it will go to this particular loop, repeat, and it is going to check whether x equal to y. In this case, x will not be equal to y, because x is the initial state and y we are adding some more extra to it. So, it will be in this particular loop until we cannot add any more states to this particular set of states y. Then it will come out from the loop and finally, it is going to return y. Okay. So, these are the three methods that we need for our model checking algorithm, because other operators can be expressed with the help of these three particular states, particular operator. So, what are the three operators that we have discussed? EU, then previous to it we have defined AF and EX. So, we now have method for checking the truth values of CTL formulas. Now, after performing the labeling for all sub formulas of phi including phi itself, we output the states where the phi is true. Okay. This is already we have discussed that if my phi is given as your AG AFP, then this is one sub formula, AFP is another sub formula, and this is the given formula. Okay. So, if we know the truth values of those particular sub formula, then only we can find out the truth values of this particular given formula phi. And in this particular case, P is a atomic proposition. So, we know the state of state where P is true with our labeling function, because our model is having a labeling function. So, this is the way we can say, and after completion of this model checking algorithm, what it does? It gives me the state of states where this particular formula phi is true. Now, in this particular case, you just see what may be the complexity of this model checking algorithm. Okay. So, the complexity basically about it is the order of f, v and v plus e. What is your f? F is nothing but a number of connectives in the formula, because if we are having n number of connectives, then we are having n number of sub formulas including the given formula in that particular CTL formula. So, we must know the truth values of each and every sub formula, then only we can look for the truth values of the given formula. So, from the primitive sub formula always we need to start. So, for that many times we have to run our algorithm. Again we are going to look for all the states that we are having, because we have to check it for all the states. Finally, we are going to return the state of state where the given formula is true, and we have to, it is nothing but a graph traversal algorithm. For every sub formula we have to traverse the entire graph, and this is the graph that we are having. It depends on the number of edges and number of vertices. So, this is a graph traversal algorithm, and we have to traverse the entire graph for each sub formula, and we have to look it for its node, okay, each node of the graph or the model. So, that is why the complexity turns up to be f, v and v plus e. So, this is a algorithm and the complexity is not that high. So, that is why model checking algorithm is promising to apply in our verification of our system design. Now, we have seen the model checking algorithm. Now, we will see how we can apply this particular model checking algorithm. So, simple example we are going to take over here, which is the mutual exclusion problem that we have. It is basically a method for our resource sharing. If a particular resource is shared by many utilities, then what will happen? We should have the access in such a way that it will be utilized properly and 2 or 3 processes should not disturb its contents. So, when concurrent processes share a resources, for example, file or database record, it may be necessary to ensure that they do not have access to it at the same time, because if this is a shared resource and it is going to access by these two systems, then what will happen? Some of the updation done by this one may be overwritten by the other one. Okay. So, to achieve it, so we have to assure it. So, mutual exclusion is one of the protocol through which we can assure this thing. So, for that we are talking about the identification of critical section. What is a critical section? If in a process a shared variable or shared resource is modified by a particular entity, then we can say this is the critical section, because if someone is doing some modification, then others should not disturb at that particular time. Okay. So, this critical section have to be accessed mutually exclusively. Okay. So, for that we are going to see how we are going to model it. So, first one we have to see how to model the system and what are the specification or what are the properties that it needs to satisfy and how to express those particular properties. So, in that particular case, already I have mentioned about a critical section where that shared resource will be modified by a particular process. So, when I am having a process, then we can say that this process may have 3 different states. For our understanding, we will say that it is divided into 3 different parts, and what are these 3 parts? One is your non-critical, trying and critical. In case of non-critical, it says that means now process in a non-critical region, that means it is not doing any work with the shared resources. Trying is a process where says that now process is trying to enter into the critical region, because if I need to access the shared resource, I am going to try for it, but if somebody else is using it, immediately I am not going to get it. So, I will just try to access it, try to access this particular shared resource. At that point, I will say that process is in the trying state. And finally, the critical state. Once the process is accessing the shared resource, then we say that it is in the critical region. So, all process can have 3 different states. And what are the possible transition that we are having? If it is a non-critical region, then always it will try to enter into the critical region if required. Once it is requesting for entering into the critical region, eventually it may try to get to enter into the critical region, and once the system is in your critical region, after completion its job, it will come out and it will be in the non-critical. So, these are the possible transition. So, these are the possible transition for process P1. Similarly, these are the possible transition for the process P2. Just so that process P1 and P2 are trying to or always access a shared resource. Now, you have to guarantee about the mutual exclusion, that both should not enter into the critical region at the same time. So, these are the 3 states we are having, N1, T1, C1, and these are the possible transition. That means we have 3 possible transition for process P1. Similarly, we are having 3 possible transition for process P2. Now, I have to look for the entire system. We are going to compose the entire system by these 2 transition system. Okay. So, one transition system is process P1, another transition system for the process P2, and now we are going to compose these 2 transition system to get our final transition system. So, final transition system will turn up to be something like that. Initially, both are in non-critical region. So, one is in your non-critical region, then it may try to enter into the critical region, other one is still in the non-critical region. Or it may happen that process P2 may trying to enter into the critical region and process N1 still in the non-critical region. From such type of scenario, it may happen that both of them are trying to enter into the critical region. Or in some cases, since it is trying to enter into the critical region, if others one is not into the critical region, then what will happen? It will enter into the critical region. After completion of its job, it will come back. So, in this particular way, I can say that after composing these things, this is the final state space we are getting it. Here, I am just writing 2 terms. One is your total number of states, and second one is reachable state. Now, in this particular case, you just see that I am having 6 variable, N1, T1, C1, and N2, C2, T2. Now, what this N1, N2 means? That means this particular state is labeled with N1 and N2. That means N1 and N2 is true over here, but the other 4 variables or state variable are false at this particular one. That means I can say that not of T1, not of T2, not of C1, not of C2. Basically, this labeling is indicating like that. That means N1 and N2 is true over here, but other 4 state variables are false at that particular point. So, total 6 state variable we are having. If we are having total 6 state variable, then what is the possible combination? How many states we are going to have? We are going to have 2 to the power 6 possible states. So, this is my entire state space, but in our system all may not be a valid state as per our design. Okay. So, for that in our system we are going to say that what are the reachable state. If you count it, then you are going to get the reachable states is 8 only, because I am designing it for mutual exclusion. So, in a particular state I should not get that both C1 and C2 is true, whatever may be the other 4 variable. Okay. So, that means whatever may be the other variables, it may be true and false. I am having total 2 to the power 4 16 different combination where C1 and C2 is true, and this is not a desired behavior for my model, for my system. So, these 16 states are not reachable. Similarly, you can find out the other also. Finally, out of 2 to the power 6, we are having only 8 reachable states in our model, and we are going to design about this particular model only. Okay. Now, what are the properties that we are going to specify and we are going to verify it? One simple example, just I am saying that no matter where you are, there is always a way to get to the initial state, and in our system we are considering this as initial state. It says whatever may be the matter, wherever you are, from any position there is always a scope to come back to the initial state. Okay. So, no matters where you are, there is always a way to get to the initial state. Okay. Now, this is basically I am saying that my system is going to satisfy this property. Now, how formally we are going to write this particular specification? We are writing this is some sort of Cripps English sentences, but when I am going to look for the truth values or correctness of this particular property, then this, if I am going to write this way, it will be difficult to check for the correctness or it will be difficult to automate it. So, we are going to capture these particular properties in a formal way, and in this particular case we are talking about a CTL, computational tree logic. So, this property can be expressed as like that in A, G, E, F, N1 and N2. So, in a particular state N1 and N2 is true, that means this is the initial state. So, wherever you are, there exists a path in future it becomes N1 and N2 becomes true, and this property should hold globally, because we are saying that no matter where you are. So, this property must hold globally. So, that is why I am having this particular connector SG. So, such this property is specified with the help of a temporal logic formula. So, whatever property we are going to check that my system should satisfy, we have to represent those particular property with the help of CTL formula. So, for such type of Michel exclusion problem, some of the basic properties it should satisfy. So, what are those particular properties? First one is called safety. So, what safety property says? Only one process to be in its critical section at any time. So, this is a safety property. Already I have said that two processes should not enter into the critical section at the same time. So, we have to assure about the safety, and it says only one process to be in its critical section at any time. Similarly, second one is liveness. What it says? Whenever any process want to enter its critical section, it will eventually be permitted to do so. Okay. So, if one particular process is trying to enter into the critical section, eventually it must get a chance. If it is not getting a chance, that means we are denying the service. So, it must satisfy this liveness property. Third one is non-blocking. A process can always request to enter its critical section. So, we say it is non-blocking because we should not put any restriction that process X should not request for the critical section at some point of time. If we put such type of restriction, then it is a blocking criteria. So, our mutual exclusion should satisfy this non-blocking properties also. A process can always request to enter into the critical section. And another property is no strict sequencing. Process need not enter their critical section in strict sequence. We should not impose any sequence. Just say that A will enter after B, then B will enter after C. We should not put any such restriction. So, it should be open. So, these are some properties that we have to always try to fulfill when we are going to design for this mutual exclusion protocol. Alright. Now, these properties now when we are going to apply the model seeking method, we have to capture those properties with the help of our CTL formula. So, some of the example I am saying, the safety properties, only one process to be in its critical section at any time. So, how we are going to specify it with the help of CTL? This is the formula that we can write. All path globally not of C1 and C2, not of C1 and C2. This must hold globally. So, that is why I am saying in all path globally not of C1 and C2. Similarly, in liveness, what we are saying, whenever any process want to enter its critical section, it will eventually be permitted to do so. So, it says that if T1, that means process P1 is trying to enter into the critical section, that it implies that in all path in future AFC1, that means from that particular state wherever you go, at least somewhere in future you should have a state where C1 is true. Okay. So, if it is trying to enter into the critical section, eventually it should be permitted to enter into the critical section. So, this is the property, and this property must hold globally. So, that is why AG. So, it talks about the process P1. Similarly, we are having process P2. So, this is what is the Leibniz properties for process P2. It is similar to this one. Now, we can write AG T2 implies AF C2. So, this is the similar property which is basically talking about in all parts globally T2 implies AF C2. That means if process P2 is trying to enter into the critical section, eventually it should get a permission to enter into the critical section. Now, how to check those particular property? So, one simple property we are just going to talk about the safety property AG not of C1 and C2. Okay. So, in this particular case this is the given model already I have seen. This is in this given model we are going to look for the truth values of this particular property, whether it is true in this particular given model or not. So, when I am talking about AG, C1 and C2, I am going to find out the state of state where this particular formula is true. Now, in that particular case you just see we do not have any operator, we do not have any method to check for the truth values of AG, but we know that there is an equivalence. So, AG not of C1 and C2 is equivalent to not of EF C1 and C2, because we have the method for EX, AF and EU. So, we do not have any method for AG. So, that means AG will be equivalent to not of EF C1 and C2. Again we are having a method for AF, but not for EF, but EF can be represented like that E true until C1 and C2. Okay. Now, you just see when I am coming up to this particular formula, we are having this is a atomic proposition and we are having a method for E until. Okay. So, we can apply this particular E until method to check for the truth values of this particular one. So, this is basically the equivalence, whatever equivalence we have used for converting that AG not of C1 and C2, just I am mentioning over here for my ready reference. Okay. Now, for this particular formula, when I am going to look into it, finally we are going to check for this particular formula, and for this particular formula you see these are the sub formulas that we are having C1, C2, then C1 and C2, that E true until C1 and C2, and finally not of E true until C1 and C2. Now, when I am going to look for the truth values of this particular formula, I must know the truth values of those particular sub formulas. That means, I must know the state of state where these particular sub formulas are true. Okay. Now, in this particular case, now we are going to see that we are having total 8 state from S0 to S7. Now, what is the state of state where C1 is true? So, this is your S3 and S6. So, in S3 and S6 C1 is true. This is the state of state where C1 is true. Where C2 is true, it is in S5 and S7. So, these are the two states where C2 is true. So, we have seen, we know the truth values of C1 and C2, or we know the state of state where C1 and C2 are true. So, these are my atomic proposition, and we are getting it with the help of our labeling function. So, these are the as per the labeling function we have labeled those particular state. Now, when I am having that C1 and C2, then what are the state of state where C1 and C2 are true? This is nothing but the union of these two states, and ultimately I am getting phi null state. So, know where C1 and C2 is true. Now, next we have to see where E true until C1 and C2. Again, if you look into the algorithm, then you will find that since this is phi, so we are going to get another null state. So, in another null state we are getting, so E true until C1 and C2 is false in all the state. So, finally, if I take the negation of it, basically what it will be there, the entire state space minus this null state, that means the entire state space is coming over here. That means, in all the states this particular C1 is C2 is true, or you can say that all part globally not of C1 and C2 is true. Okay. So, that means the given specification is valid in my given model. that means safety property is assured. So, similarly I can talk about the liveness property. AG T1 implies AFC1. Now, again I do not have any method for AG in our complete set of operators. So, finally AG will be converted to EF, and again we do not have method for EF. So, it will be converted to ET until this thing. So, finally this is the formula. We are going to look for the truth values of this particular formula in our model. So, that means what are the sub formulas that we are having? T1 C1, T1 C1 AFC1, then T1 implies AFC1, then negation of this particular T1 implies AFC1, then E true until these things, and finally negation of this particular E true until not of T1 implies AFC1. Okay. So, we have to look for the truth values of those particular sub formulas to get the set of state where this given formula is true. So, already we have seen that we have to repeat this particular operator until no sense. So, now how we are going to do it? First find out the state of state where T1 is true by looking into these things. T1 is true in your S1, then S4 and S7. These are the state where T1 is true. So, we are collecting the state of state where T1 is true. Similarly, we are collecting the state of state where C1 is true. Now, we are going to look for the state of state where AFC1 is true. Now, as per our semantics, we know that wherever C1 is true, AFC1 will be true in this particular state. So, the S3 and S6 are the state of states where AFC1 is true. This is the initial point. Now, we have to traverse this particular state space to find out the states of state where this particular formula is true. Now, how we are going to say? It is in all path in future. That means, we have to know this formula will be true in all the predecessor of S3 and S6. Okay. If a predecessor is there and if it is coming to these two states, then we can say that EF may be true in those particular states. So, we are going to say that AFC1 will be remain true in S3 and S6 only, because we cannot collect any other state, because if you say that S3, what is the predecessor of S3? S1. When I am going to S1, you just see that here AFC1 is true, but in the other state in S4 AFC1 is not true. So, this will not come into the picture. Okay. Since it is not coming into the picture, similarly, if I am going to have this particular S6, so what are the predecessor? One is your S3 and S4. S3 is already in me, but in case of S4, in the others transition we do not have C1. So, this will also not come. So, we are not adding any new mode state to these particular sets. Okay. Since we are not adding any more states, so we not to go further, because there is no sense now in this particular set. Now, these are the set of state where AFC1 is true. Now, after knowing the truth values of AFC1 and T1, then we can look for this particular formula. T1 implies AFC1, and this is nothing but negation of T1 or AFC1. Okay. So, now what are the states? Negation of T1. We know the state of state where T1 is true. So, in case of negation, the state of state where it is not true. That means, apart from S1, S4 and S7, all other things will come S0, S2, S3, S5 and S6. Okay. So, these are the states where T1 is true. So, these are the states where T1 is not true. This one union this particular state AFC1, S3 and S6, S3 and S6 is already there. So, these are the state of states where T1 implies AFC1 is true. Next, we have to see what is the negation. So, negation finally this is not there. So, I am getting S1, S4 and S7. Now, E, P until Q, this is the final operator that we are going to use. So, it says how we are doing it. Okay. So, now we know these are the states where S1, S4 and S7 not of T1 implies AFC1 is true. So, E, T until not of T1 implies AFC1. So, in that particular case these are the state of state where this particular sub formula is true, not of T1 S4 not of T1 implies AFC1. So, this is the label any state as if labeled with Q. Now, our Q is that given sub formula. So, these are the state of state that I am getting initially where not of T1 implies AFC1 is true. Now, I am going to repeat this particular process, then what I am going to get considering S1, S4 and S7. When I go into the next level, then we will see the predecessor of these three things, then S0, S2 and S6 will come. So, from S1 I am having a predecessor S0, so S0 will come into picture. From S4 we are having a predecessor S1 and S2, S1 is already there, so S2 will come into picture, and from S7 we are having predecessor S4 and S5, S4 is already there, so S5 is coming into picture. So, now with this particular state of state again we are going to traverse this particular transition system, then we are going to find that S3 will come into the picture, then finally S6 will also be added into the system. If I just look into the predecessor, because from S0 this is a predecessor and from S6 it is a predecessor of S4. So, finally, these are the state of states that we are coming over here. Now, next we have to look for the negation of these things. So, what is the negation of these things? It is talking about the null set. That means, it is returning me a null state. That means, in none of the states the given property is true. So, what it means? That means, whatever I have modeled, the Leibniz property is not going to ensure. Okay. So, what is a Leibniz property? If someone is trying to enter into the critical section, it should eventually be permitted to enter into the critical section. This is the property that we are trying to check. But here, whatever model we have designed over here, we have seen that it is not true. It is, this property is not satisfying. So, why it is not satisfying? Now, we have to see, because finally it is giving me the empty set or null set. So, it is not true. And what is not true? The Leibniz property. Now, since it is a small system, now what I can see, I can inspect it and I can find out what may be the possibility. But in model checking method, when we implement it, it is giving me another benefit also. When the formula is true, then it is going to give me the state of states where the given formula is true. But if it is false, now it is turning up to be like that, it is false, then what will happen? It will give me a counter example. It says that if you follow this particular execution trace, then the given specification is not true. So, then we can concentrate on those particular execution trace to check why it is not true and what modification I need to do in my model. Okay. So, in this particular case, what counter example it will give? So, we are saying that if it is trying to enter into the critical section, eventually it should be able to enter into the critical section. So, if I look into it, I can inspect it, but model checking method is going to give me the counter example, and what counter example it will give? It will give me this particular counter example. Okay, that means if I am in state S1, it is trying to enter into the critical section, I am having a transition to S4, from S4, because both are trying to enter into the critical section. So, it is entering into the critical section for process 3.2. So, if it goes in this particular loop forever, okay, then what will happen? That it is not process P1 is not going to enter into the critical section, because either it can enter via this particular path or it can enter via this particular path. So, this is the region. So, similarly, if I look into AG T2 implies AFC2, which is also a Leibniz property for the process P2. Again, our model seeking algorithm will say that it is false, and it will give me the counter example of this particular part now. So, it is T2 is tying into the critical section, but it is coming over here and it is going back to this thing. So, it will remain. So, now what will happen in this particular case? It is giving me the error that your specification is not true, because it is in some condition, in some situation it is going to fail. So, in that particular case I can revisit it and I can modify my model to break those two loops, so that always it is going to assert it. Or there is another way you can reason about it. You can say that though from here I am having two different possibilities, these particular possibilities may not occur always, but it may eventually get a chance to come into this particular path. So, I may consider this particular scenario also, because it may happen that when I am coming back to this particular point, N2 is not trying to enter into the critical section, then eventually N2 will remain in N2, process P2 will remain in the state N2, and eventually it will come to this particular part and it is going to get a chance to enter into the critical section. So, I can reason in this particular way and I can accept this particular model, and I say that I am going to implement this particular model itself, because such type of scenario is going to happen will be rare. But if I do not want to take chance, then what will happen? I will relook into my design and I will try to break these two loops. Okay, it is possible, because now I have to make some more refinement to my model, so that these two loops can be broken. So, if such type of scenario is not there, then finally what will happen? After breaking these two loops, if I apply the model seeking algorithm again in my new model, then it may happen that it will say that yes, this given formula is true in your system. So, this is the way we are going to look for the formal methods to check for our specification in our design. So, what are the things that we are having over here? You just see, we are trying to design a system. So, while we are going to trying to design a system, I will look for the design issues and going to have a design, because finally my design will be some sort of your finite search system. So, that system will be abstract with my formal methods. So, I am going to get such type of model. Once I have the model, then I know the desired properties to be satisfied. I can say these are the specification of my system that I am going to design. Okay, in that particular case, we look for those particular properties, and those properties will be captured or can be converted to CTL formulas. Okay. Once I get a CTL representation of those particular properties, then I use our model checking techniques. The way we are doing over here, we give the models and we give the CTL specification or CTL property, and model checking algorithm is going to check for the correctness of those particular CTL properties. If it is true, then system is going to return the truth value as true, and we will be happy that okay, my design, the model is satisfying this particular requirement. If it is not true, that model checking algorithm finds some error, then it says that no, whatever specification you have given, it is not true, but along with that it will give me a counter example. That is, it will show me an execution trace. By going through this execution trace, the given property will not remain true or will not be valid. Then as a designer, what I can do, I will concentrate on those particular parts and I will try to redesign that particular part. The way I am saying that somehow I have to break this particular loop. So, somehow we are going to, or we will redesign that particular part and try to come up with a new design. When I am coming up with a new design, then again I will repeat this particular formal methods, model checking techniques, and eventually my design is correct, my model checking method will say that yes, it is true. So, once I formally check the properties in my model, then we can go for the next level of my design, embedded system design, then we can go for the implementation and other issues of the design. Okay, with that I am concluding today's lecture. Thank you very much.